Okay, so in this short video, I'm going to briefly walk you through our next OS 161 project, which is about thread-based synchronization, where you will be asked to implement a synchronized traffic intersection within the context of OS 161. Okay, so first of all, a few tips and tricks. So first of all, the most important thing is to get familiar with the code that you're going to touch, right? So in this specific example, in our next project, which is about project 1B, so you will be able to you will be touching the code within specifically thread directory, and also you will be looking at, for example, slash MIPS. Especially, you will be interested in taking a look at implementation within SPLC, because this is one of the most important piece of code that is used to implement interrupt disabling and interrupt resuming. Okay, and besides that, so it would be really helpful if hopefully you are already familiar with the following commands in a Linux box. So you should create like multiple panes or windows, multiple SSH sessions to log into the Zeus server. If you want to search for a specific file with a specific file name, you could use this command called find. Okay, and also if you want to search a specific like string pattern or regular expression, you could use grab to search for the occurrences of that specific pattern that you provided as a parameter, a command line argument to this grab tool. Okay. And one thing that I want to, again emphasize, even though I have mentioned this like previously, is this Zeus cluster. It consists of two nodes, right? So whenever you SSH and log into it, the load balancer tries to, randomly assign you this particular session to one of these two Zeus servers. If you want to do this two-window based GDB debugging, you need to make sure that both of your SSH sessions are logged into the same Zeus server. So it's either Zeus 1 or Zeus 2. So if you want to try to connect from Zeus 2 for your GDB client to connect to the GDB server running on Zeus 1, so this won't work because GDB by default doesn't support cross-network debugging. Okay, so these are the several common tips and tricks. Hope you've already known about at this point of time. So the core content of the next project is to implement thread-based synchronization. But before that, let's briefly talk about the thread abstraction, right? So in the context of OS 161, the thread is implemented as a really simple thread library. And the thread library consists of a data structures, which is the thread struct, as well as a few important thread APIs. So the data structure used by the thread library to store the miscellaneous, hardware-specific thread context is called a thread control block. Even though it has a name of T_PCB, but it's essentially thread control block, but instead of process control block. And all the other important information for a single thread is defined in the thread structure. Okay, so here this slide, it shows the struct PCB as well as struct thread. So at the top half of the slide, it shows the hardware-specific context information stored within PCB, which is kind of less interesting in the next project. But on the bottom half of the slide, it shows the what exactly the struct thread stores. So first of all, the very first field is the struct PCB, right? And next, it has a char string, which is used to store the specific the name of this particular thread, and also it keeps track of an opaque address, which is called T underscore sleep address, right? This is used for synchronization purposes. For example, if this particular thread want to wait for a particular semaphore, it sleeps on this semaphore, so it just pass in the address, the pointer, essentially the address of the semaphore, and then the thread will just be sleeping up on this opaque address. And the next field is the pointer, T underscore stack, which is a pointer that points to the thread stack. So far, these are all the private thread members, and the next set of fields within struct thread, they are essentially public thread members, which are exposed globally to other threads as well as to the operating systems. For example, the T underscore VM space, which is a pointer that points to the address space structure, which is again less interesting if we're talking about this particular project. Okay. And the next one, which is completely out of the scope, because basically throughout this semester we won't be touching the last field. Okay. So how is the a threading module, the thread library, started within OS 161? So the thread module is started by this function, which is called thread bootstrap. So this is where the operating system, OS 161, start the whole thread functionality. And the operating system uses a global variable, which is called curthread, to keep track of the current actively running thread under target. And recall that OS 161 is just a simplified toy-like pedagogical operating system prototype, which simulates a single core CPU, which means this particular system simulated by OS 161 has one and only one single core. So it could use this global variable, which is called curthread, to just keep track of this, the current actively running thread. Okay, it was initialized and declared within curthread.h, the header file. And as I've mentioned, all the other thread-specific information, both private and public, they are stored within the struct thread. So recall that in our lecture, we've talked about context switch. So the whole process, at high level, the context switch process starts with operating system trying to, save the context information, for example, including the CPU context, the memory context, and the storage context for the previous process or thread that operating system is planning to put into a sleep, and then restoring the context information belonging to the next interested process or thread that operating system is planning to assign the CPU cycles. Okay, so in this slide, it talks about the process of you know um, saving the context information for the currently running thread. So as you can see, these many memory word save instructions. So these are all just to save the important register values into the corresponding locations within the a thread memory space. Okay, so this is to just save the context information for the currently running thread. And the next slide shows the second half of the context switch process, which is to restore the register values for the next thread that operating system plans to put it back on. As you can see, this LW, all these load memory word operations, they are essentially just read into the memory and then try to read the already saved old context state information from the next thread's kernel stack into the CPU register and make it ready to actively run. So this is the context information, context switch information. So this slide, it lists these several thread-related interfaces. So the very first important interface is called thread fork. So this is where an OS/161 thread gets created. It takes in a few parameters. The first one is a string-based thread name. The second and third parameters are essentially the arguments that you want to pass to this newly created thread. And the fourth field is essentially the function pointer that points to this thread's main body, the logic, the thread routine. And we have the last parameter, which is a pointer, which is used to store this thread return value. So this is the thread fork. Why it's called thread fork is because so initially this thread fork API is used to create a new thread, and as you will see in the next couple of OS/161 projects, you will be essentially augmenting and enhancing the thread fork API so as to construct a process creation API. So which is basically to build the process abstraction on top of this initial original thread abstraction within OS/161. So this is the thread fork, and if you want to and quit a specific thread, you should call thread exit, and it has no parameter. And the third API is called thread yield, is just to yield the CPU and let the other thread run. And we have another thread which has similar functionality, which is called thread sleep. There is some subtle difference which I will be talking about in the next couple of slides, but the effect of these two system two function calls are more or less the same, right? To just let the other thread which are ready to let the scheduler pick whatever other thread gets ready and go ahead to burn the next available CPU cycles. And we have the last a thread API, which is thread wake up. This is used to unblock whatever sleeping threads, but at the head of the sleeping queue. Okay. So let's first take a look at how to create a new thread within OS/161. So as I've already mentioned, this thread fork, it's So why it has this suffix, which is called fork? This is essentially because originally OS 161 exposes a thread abstraction, and as you will see in the next couple of projects, you will be essentially implementing a process abstraction on top of the thread abstraction. So that is why the thread fork, it's kind of like a single API that tries to really merge these two different abstractions, the thread abstraction together with the process abstraction. So it combines thread with underscore and then fork, but it doesn't matter. So far, within the context of this particular thread synchronization project, the thread underscore fork is really just to create a new thread. Okay. So the question is, what if you wanna pass more than 2 arguments, right? Because if you take a look at the signature of this interface, it has only 2 fields: the second parameter and the third parameter. And the second parameter is an opaque pointer, which could be like any type of data, and the third parameter is just a long integer, unsigned long integer. So the question is, what if you want to pass in more than 2 parameters, right? Well, so this could be supported by embedding more information within this opaque pointer. You could pass in whatever structure that you want to create, right? But just cast it to this generic pointer. So this is how you exactly pass more information as the arguments to the newly created thread. So this slide shows a piece of code to just showcase how exactly you could use thread fork to create new threads. So the code is located within kern/assignment1/catmouse.c. This is a simple user level program, which is try to simulate this cat and mice game. So as you can see, you just basically the control just essentially enter into a for loop, and during each iteration of the for loop, it tries to create a new mouse, right, by calling the thread fork, and it takes in the very first parameter, which is a string-based name. Is a name that you want to assign to this newly created thread. In this particular case, it's called mouse simulation thread, and it just simply skip the second parameter and simply pass this index as the a third parameter, which is the index of this thread, and then specify the implementation of this particular thread, which is called mouse simulation. Okay, so this is a function pointer that points to the implementation of this particular thread somewhere else. Okay, but definitely take a look at this this code example to just get a sense how the these various different thread related APIs are used. Okay, and then the second part of this code, it implements some sort of synchronization logic by using the built-in semaphore interfaces. In this case, it calls P, which is essentially semaphore wait. Okay, and we'll be talking more about this semaphore within OS 161 in the next couple of slides. So scheduling, I recall that last lecture we've just get started on this new topic, CPU scheduling. In the context of OS 161, it uses a really simple CPU job scheduling policy, which is first in, first out, FIFO. So the scheduler maintains a global queue of threads. It uses a queue to keep track of whichever threads gets ready to run, and this queue is called ready queue. And the logic is pretty simple and straightforward. Just pick whatever gets ready from the head of the queue. The first ever thread within the ready queue will become the next running thread. And whenever there's a context switch, and this the context switch will be enforced and triggered by this timer hardware interrupt. And whenever there's a, let's say, timer context switch, and this particular running thread will be moved to the end of the ready queue, and the operating system scheduler will go ahead and pick the next the new first thread and allow it to run from the ready queue. And another thing is the whenever you create a new thread, this newly created thread will be placed at the end of the ready queue. Okay. And so this slide is talk about so how to enforce mutual exclusion generally. So we've talked about how to really guarantee mutual exclusion by using various different approaches in our lecture, right? So the first technique that we've talked about was using a binary spin lock. And besides that, so we also talk about how to really implement a binary lock by using hardware facilitated approach. For example, the example that we've talked about, Tesson set, and there are some other like hardware based instructions which is called compare and swap, and you could use other synchronization primitives, for example, semaphore and condition variables, as well, to just guarantee that at any single point of time within the critical section, there is only one thread or only one process that could be within the critical section. Okay. So, and recall, so this is again kind of, to just repeat whatever we've already discussed in our lecture. So, in our lecture, we've talked about this single trick, which could be used to implement a mutual exclusion, right? Which is to disable interrupt. So let's assume we have a uniprocessor, which means this system has only one processor and one CPU core, and which also kind of implies that only one single thread at a time is actually running. And if this running thread is executing within a critical section, you must guarantee mutual exclusion, right? So within the critical section, you must guarantee that so-called atomicity. So you cannot preempt this running thread from within the critical section, right? And the operating system must not schedule a different thread while at the same time another thread is within the critical section. So in other words, you must guarantee this all or nothing atomicity property. So, and this, operating system preemption, where the context switch will be performed, is pretty much because of this the hardware timer-based interrupt. So we need to guarantee that on a single uniprocessor system, you must disable this interrupt so that operating system won't just accidentally sneak in and mess up this all or nothing atomicity property. So with that, you need to have some mechanism so as to disable the interrupt before a thread enters into the critical section, and then re-enable the interrupt when the thread leaves the critical section. This is how exactly OS 161, this pedagogical operating system, implements synchronization primitives. For example, semaphore is the semaphore operating system OS 161. A built-in semaphore is implemented using this approach. So there are these several interfaces that are interesting that could be used to implement interrupt disabling and reabling mechanism. So the very first one is called SPL high. And this is interface which is used to disable the interrupt. And in order to bring it back up, you need to call SPLX. So the SPL high will return the current interrupt level, which is a 4-byte integer, and then you need to memorize this integer and then use SPLX to resume the interrupt level to the previously recorded one, before the interrupt was disabled. Okay, so please definitely take a look at this implementation detail under kern/arg/mips /include, and there's a header file which is called spl.h. Okay, it's located over here. So just briefly talk about the pros and cons, as we've already had a detailed discussion about this good and downside of disabling interrupts. First of all, advantage. It's straightforward. It's pretty simple to implement, right? And it just works well for any number of concurrent threads if the target system is a uniprocess system which has only one single CPU. But it comes with a bunch of disadvantages, right? The very first important the very first critical disadvantage is that if you prevent all the preemption, not just the preemption, that would threaten the a critical section. And if you ignore the timer interrupts, it has some side effects, right? So for example, you are being faced with the risk of losing potential interrupt requests, right? And also, if we're talking about like real world operating system, this single operation to disable and re-enable interrupts is pretty costly, And another severe downside of this approach is it won't work if we're talking about multiprocessor, like the processor has more than one CPU core, right? And then operating system is free to schedule whatever thread, concurrently running thread on the second core, no matter whether you disable the interrupt globally or not. The operating system has a freedom to schedule whatever on a different core, and this just will simply break this mutual exclusive property that you want to enforce upfront at the first place. Okay. So let's next take a look at the semaphore implementation in the context of OS 161. And recall that the semaphore is a synchronization primitive that could be used to enforce mutual exclusive requirements. And it could be used to solve a range of a synchronization problem, for example, the producer-consumer problem, where the shared buffer has multiple slots, and you could use semaphore to try to memorize a state of different slots within your shared buffer. And we've already seen that semaphore has two simple APIs. The first one is semaphore wait, which what is essentially doing is decrement the semaphore value, and whenever the value becomes negative, put the caller thread into a sleep. So this is associated with this semaphore wait API is also called P in the context of OS 161. This is essentially semaphore wait. Okay, what it does is essentially decrement the value. And another API is called semaphore post. So what it does is it performs self-increment on the semaphore value, and then wake up one of the threads if there are more than one or multiple threads that are sleeping on the semaphore. And corresponding in the context of OS 161, semaphore post has a different name, which is called V. Okay. So as we've already seen, there are these two different kinds of semaphore. The first one is counting semaphore. The second one is the binary semaphore, where it has exactly two different states, 0 and 1. So we can use this binary semaphore to kind of simulate the behavior of a binary log, which is essentially a log. We use it as a log. Okay. So why are we looking at this? Obviously, you will be implementing the most important thing that you should note here is you're implementing the locks logic by referring to the implementation of OS 161's semaphore implementation. Okay, so within OS 161, semaphore is essentially using this interrupt disabling and re-enabling technique, and this is the exact technique that you should use as well, so as to implement the lock. The lock APIs. Okay. So the next couple of slides talk about the underlying implementation of OS 161 semaphores. So at the very top of the slide, it shows the struct semaphore, which has exactly two fields. The first field is the name of the semaphore, which is a string. Char-based string. The second field is a volatile integer, which is essentially a counter, right? Recall that semaphore is just essentially a counter, and it uses the second field to keep track how many threads, let's say, have already sent the a let go signal and so on. So in order to create a semaphore, you need to use sem_create, which takes in exactly two parameters. First one is the name of the semaphore, and the second one is the initial value that you want to initialize the semaphore. And another two important APIs are P and V, which are corresponding with semaphore wait and semaphore post, respectively. And if you want to destroy, after done with using the semaphore, you could call semaphore_destroy to just destruct it. Okay, so the definition of the declaration of the semaphore correlated data structures and APIs is within this header file under kern/include, and the specific implementation of semaphore is within this kern/thread/sync.c file, and this is the same source file where you want to put together implementation for the lock as well. Okay, within the same a source file. In the context of OS 161, so as part of this project, you will be asked to implement another important sync primitive, which is called log. So the OS 161 log also exposes a set of important APIs. The first one is initialization API, which is log create, where it just takes exactly one single parameter, which is the name of this particular log. And the next two important APIs are a log acquire and log release. In order to grab the log, you need to call log acquire, and to just release the log as owner of the log, just call log release, as we've already discussed in our lecture. Right? So note here, the implementation of the log is not fully done yet. So what you really want to do is you want to finish the implementation of the log. by referring to the implementation of the semaphore within OS 161. So this slide, it shows a really simple piece of code to demonstrate the usage of semaphore. So in this example, you initialize a semaphore just like a binary, as a binary log. Over here, you just assign the value of the semaphore as 1, right? So to indicate that this semaphore has exactly 2 different states. And whenever you want to enter the critical section, just call P on this S, which has exactly the same effect of calling lock acquire, and then enters the critical section. And then after done with access to the shared resource, whatever, within the critical section, before leaving the critical section, just release a log. In this particular case, just call semaphore V, which is essentially semaphore post, to release a log. Okay, so this is how you provide this mutual exclusion guarantee by using a semaphore. So next, let's take a look at the exact implementation of OS 161 semaphore. So the first API is semaphore wait, which is also called P in the context of OS 161. Okay. So here, enter into the body of the function, you declare an integer typed variable, which is called SPL, which will be used to, to disable and re-enable this interrupt of operating system. And over here, you insert an assert statement just to check that interrupt is at the is not already being disabled. Okay, just for robustness consideration. And then the most important thing that you should pay special attention on is this SPL high API, which is used to disable interrupts, and make sure to take a look at the internal implementation. And it has a return value, and you will need to use this already declared integer type variable, which is called SPL, to capture the return value, right? To memorize its previous interrupt level, and then disable interrupt by calling SPL high, and then enter the critical section. And you enter the while loop over here, and you just keep checking. So the condition of the while loop is if the value of the semaphore is equal to 0, it means if equal to 0, you need this caller thread needs to really fall into the sleeping state, right? By just calling thread sleep on this semaphore, where you just pass in this opaque address. This is where the thread is sleeping on. And then let's say some other thread calls V, which is semaphore post. This will wake up this thread, and then the control flow loops back and recheck the state to see if the state is still, if the value is still 0, and if luckily there's no other competing thread. So that thread which sent the signal, which calls V, right, will do self-increment on the counter and make the counter greater than 0. And luckily, this sleeping thread will just simply, because this condition of the while loop is not satisfied, it will just directly jump out of this while loop and then perform self-decrement on this semaphore value. And then before leaving the critical section, you need to make sure that you resume, re-enable this interrupt by using the value you've just memorized. Okay, so this is the semaphore wait, which is P, right? But before moving on to semaphore post or V, so let's just briefly walk through this the rest of the thread APIs. So these are these two that we're especially interested in. The first one is thread sleep. The second one is thread wake up. So the thread sleep is just simply blocking the calling thread on the address provided as this single parameter. And thread wake up is used to unblock any threads, one or multiple threads that are sleeping on this address, which is passed in as this single parameter, which is called address. Okay, so note here, thread sleep is similar to thread yield, but there are subtle differences. The calling thread, if calling thread sleep will just voluntarily gives up the CPU, and the scheduler will choose a new thread to run. So this is what's in common between these two different APIs. But what makes these two different APIs different is that after thread yield, the calling thread is again within the ready mode, within the ready state. It's again ready to run, but just simply put itself at the end of the ready queue, at the tail of the ready queue. Okay. But differently, the thread sleep will make sure that the calling thread transit from the ready state, from the running state to this block state, and should not be scheduled again until it has been explicitly unblocked or woken up by another thread, which calls this corresponding API, which is called thread wake up. So these are the fundamental difference between these two different APIs. Okay. So in the context of OS 161, each and every thread, follows this a simple three-state state transition graph. So all the threads get started with this ready state, and it transits between the three different states, right? Whenever it's the scheduler, so the scheduler will just pick the first ready thread from the head of the ready queue. So we have a queue over here, and allow it to run. So this thread transits from the ready state to the running state. And whenever this running thread calls thread sleep, right? Need to wait for some resource on some event. The operating system will transit the state from the running state to this block state. And whenever some other thread calls thread wake up, and that thread will just wake up this block thread, and the operating system will just drag this thread from this block queue to the end of the tail of this ready queue. Okay, so this is we've talked about this. Recall that in our lecture. So then moving on. So this slide, it talks about the implementation of the semaphore post, which is called V in OS 161. It's also located at kern/thread/sync.c. So its main logic is also straightforward. So before entering the critical section, you need to first disable the interrupt by calling this SPL high and record the previous interrupt level in this variable. And then you'll enter the critical section and perform self-increment on this semaphore value. And then you call this thread wake up on this opaque pointer to wake up all the threads, right? One or multiple. If there are more than one threads that are sleeping on this semaphore, just wake them all up. But eventually, there would be only one thread that could go ahead and get scheduled by the operating system scheduler, and the rest of them will put themselves back into sleep. Why is that? It's because recall that in the implementation of the semaphore, there's a while loop, right? And whenever some thread gets woken up, it will further loop back and recheck the state. The state is check the counter, whether the counter is equal to 0 or not. if it's again equal to 0, it means some other competing thread has already passed the critical section and perform self-decrement on the value again successfully, and then this thread unfortunately need to stay within the while loop and keep calling this thread sleep and put itself into the sleep again. Okay, so this is roughly how, let's say, multiple threads interact with each other with this thread wake up and thread sleep APIs. And then before leaving the critical section, you need to make sure that it calls SPLX to resume the interrupt, to re-enable the interrupt. Okay, so this is how Semaphore post implemented within OS 161. So the last slide, this shows how to test your work, how to test your implementation. Well, so if you run sys 161 kernel, and then it will prompt with a question mark, right? Just type question T. It will just list all the available tests within the context of OS 161. And the very first thing that you want to test, you want to make sure that your implemented clock is correct, right? Just use SY2 to test, the correctness of your log implementation. And we have some other tests. We have another test which is directly associated with the stoplight traffic intersection testing. So use that to test your traffic light synchronization problem. Okay. And next